Our world runs on software. From the apps on our phones to the systems controlling traffic lights, it's everywhere. We rely on this invisible code to work flawlessly, but what happens when it doesn't? Glitches, errors, crashes, these are all symptoms of software gone wrong. Software testing is the unsung hero, working behind the scenes to prevent these disasters and ensure that our digital experiences are smooth and reliable. Software testing is more than just finding bugs, it's about ensuring quality. It's about building software that is not only functional, but also secure, efficient, and user-friendly. At its core, software testing involves two main activities: verification and validation. Verification ensures that the software meets the specified requirements and is built correctly, while validation focuses on whether the software meets the user's needs and expectations. Imagine launching a new e-commerce website, only to have it crash on Black Friday due to a software bug. The financial losses could be devastating. Or consider a medical device malfunctioning during surgery because of a software error. The consequences could be life-threatening. Software failures can have far-reaching consequences, impacting not just businesses, but also individuals and society as a whole. By investing in robust software testing practices, organizations can minimize the risk of costly and potentially dangerous software failures. Software testing, while requiring an upfront investment, ultimately saves time, money, and a whole lot of headaches in the long run. By identifying and addressing defects early in the development cycle, software testing helps to avoid costly rework later on. Moreover, robust software testing leads to a better user experience, ensuring that users have a smooth and enjoyable experience with the software. In today's digital age, trust is paramount. Users expect software to be reliable, secure, and to perform as promised. Software testing plays a vital role in building and maintaining that trust. By investing in comprehensive software testing, organizations demonstrate their commitment to quality and security, building trust with their users. Ultimately, software testing is an investment in the long-term success of a software product and the organization behind it. Imagine software testing as a vast toolkit, filled with various instruments, each designed to examine and analyze software from different angles. These testing types can be broadly categorized based on their scope, approach, and objectives. The key is to select the right combination of testing types to ensure comprehensive coverage and maximize defect detection. Imagine building a house. You wouldn't wait until the entire structure is complete before checking if the individual bricks are strong and well made, would you? Similarly, in software development, unit testing focuses on testing the smallest units of code, called modules or components, in isolation. Unit testing verifies that each unit functions correctly in isolation, ensuring that the foundation of the software is solid. Building on the house analogy, imagine you've tested each brick individually and confirmed their strength. Now it's time to assemble them into walls, connect those walls, and ensure that the entire structure holds together. This is where integration testing comes in. It focuses on testing the interactions between different units or components of software to ensure they work together harmoniously. By thoroughly testing these interactions, integration testing helps to identify and resolve defects that might not be apparent during unit testing. Imagine a watchmaker meticulously crafting each tiny gear spring and screw of a complex timepiece. Before assembling the watch, they carefully inspect and test each component in isolation to ensure it functions flawlessly. This meticulous approach mirrors the essence of unit testing in software development. By testing them in a controlled environment, separate from the complexities of the entire system, developers can pinpoint and fix defects with greater precision. Imagine constructing a bridge, piece by piece, with each component rigorously tested for strength and stability before being added to the structure. Similarly, unit testing acts as a safety net in software development, providing a robust foundation for building reliable applications. This safety net gives developers the confidence to refactor code, add new features, and fix bugs without the constant fear of introducing regressions. Effective unit testing requires a strategic approach to ensure comprehensive coverage and maximize defect detection. One common strategy is black box testing, where the tester focuses solely on the inputs and outputs of a unit, without any knowledge of its internal workings. Another strategy is white box testing, which involves examining the internal structure and logic of the code being tested. Think of unit testing like a toolbox filled with different types of tests, each designed to examine specific aspects of your code. One common type is the functional test, which focuses on testing the output of a function or method given a specific input. Another type is the state-based test, which verifies that the internal state of an object changes correctly after certain operations. Section 2. Pros reaping the rewards of unit testing. Imagine catching software bugs early, before they snowball into major headaches. Unit testing acts like a vigilant guard against defects from the early stages. This early detection saves time, resources, and reduces debugging time. Isolating and testing individual units helps quickly identify and fix errors. This prevents bugs from multiplying and becoming harder to track. Early bug detection translates to reduced development costs. Unit testing promotes cleaner, more maintainable code. Cons: navigating the limitations. Unit testing has limitations. It can't catch every bug or simulate complex interactions in a system. Issues like network latency or database inconsistencies might be missed. Poorly designed tests can give a false sense of security. Despite these, the benefits outweigh the drawbacks. Be aware of limitations and integrate unit testing strategically. Integration testing. Assembling the puzzle. Imagine building a car. You could meticulously test each individual component, the engine, transmission, brakes, in isolation. But until you assemble them and see how they interact, you can't be sure the car will run smoothly. This is the essence of integration testing in software development. Unit testing focuses on the smallest units of code. Integration testing takes a broader perspective, examining how these individual units work together as a cohesive system. It's like taking all those meticulously crafted car parts and putting them together to see if the engine starts, the gears shift, and the brakes hold. The primary goal of integration testing is to uncover defects that arise from the interaction between different components. These defects, often related to data flow, communication protocols, or interface compatibility, might not be apparent during unit testing. Integration testing typically occurs after unit testing and before system testing. It acts as a bridge, ensuring that the individually tested units function harmoniously when combined. By catching integration-related defects early on, we prevent them from snowballing into larger, more complex issues during later testing phases. Strategies for seamless integration. Think of a conductor leading an orchestra. Each musician practices their part individually, but it's the conductor's role to ensure they play in sync, creating a harmonious symphony. Similarly, integration testing requires strategic orchestration to ensure seamless interaction between software components. One common strategy is top-down integration, where testing starts with the highest-level modules and progressively integrates lower-level modules. It's like building a house from the roof down, ensuring each layer integrates seamlessly with the one above it. Another approach is bottom-up integration, where testing begins with the lowest-level modules and gradually integrates higher-level modules. This is akin to building a house from the foundation up, ensuring each layer is solid before adding the next. There's also Big Bang integration, where all modules are integrated simultaneously and tested as a complete system. This approach, while seemingly quick, carries higher risks as it becomes challenging to isolate defects when they arise. The choice of integration testing strategy depends on factors like project complexity, dependencies between modules, and risk tolerance. A well-defined strategy ensures systematic testing of all integration points, minimizing the risk of overlooked defects. Section 3. Types of integration testing. A closer look. Imagine a detective investigating a complex case using different techniques to gather evidence from various angles. Similarly, integration testing encompasses different types, each designed to uncover specific defects arising from component interactions. Component integration testing focuses on interactions between software components that make up a larger subsystem. It's like testing the engine and transmission together to ensure they work in sync before integrating them with the rest of the car. System integration testing takes a broader view, examining interactions between different subsystems within the entire system. This is like testing the entire car engine, transmission, brakes, electrical system to ensure they all function together seamlessly. External system integration testing focuses on interactions between the system under test and external systems, such as databases, APIs, or third-party services. This is like testing how the car interacts with the road, traffic signals, and other vehicles in a real-world environment. By employing a combination of these integration testing types, we can ensure comprehensive coverage of all interaction points within and outside the system, minimizing the risk of integration-related defects impacting the software's functionality. Section 1. Pros: Unveiling the power of integration. Imagine assembling a jigsaw puzzle. You can meticulously examine each piece individually, but the true beauty emerges only when they connect, revealing the bigger picture. Integration testing, in a similar way, unveils the true potential of software by ensuring its components work harmoniously as a unified whole. One of the primary advantages of integration testing is its ability to detect defects that unit testing might miss. These defects, often related to interface mismatches, data inconsistencies, or timing issues between components, only surface when those components interact within a larger system. By identifying and resolving these integration-related defects early on, we prevent them from cascading into larger problems during later testing phases, or worse, in production. This proactive approach saves significant time and resources, as fixing defects becomes exponentially more expensive the later they are found. Moreover, integration testing provides a higher level of confidence in the software's functionality. By verifying that different modules and subsystems work together as intended, we gain assurance that the software meets its specified requirements and behaves as expected in a real-world environment. Integration testing is crucial for robust software but comes with challenges. Like a complex maze, it requires careful planning and execution. Numerous integration points increase testing complexity. Prioritize testing based on risk and criticality. Robust test environments are essential. Setting up these environments can be resource-intensive. Debugging integration defects is challenging. Careful analysis of logs and data flows is needed. Despite challenges, integration testing is beneficial. Effective strategies and collaboration lead to well-integrated software. Imagine a chef carefully balancing different flavors to create a delicious meal. Similarly, software quality requires balancing unit and integration testing. Unit tests catch early defects. Integration tests ensure components work together. The key is finding the right balance for the project's needs. Leverage both testing types to ensure comprehensive software quality. Imagine two sides of a coin, each representing a crucial aspect of software testing. Unit testing, like one side, focuses on the individual components, ensuring their intrinsic quality. Integration testing, like the other side, examines how these components mesh together, guaranteeing the system's overall harmony. Let's draw a clearer picture of their differences. Unit testing dives deep into individual code units, tested in isolation. It's like examining each ingredient of a cake separately, ensuring its freshness and quality. Integration testing, however, steps back to see the bigger picture, testing how those units interact when combined. It's like baking the cake and tasting it to ensure all the flavors blend well. This table highlights their distinct roles. Unit testing, with its narrow scope and fast execution, acts like a safety net during development. Integration testing, broader in scope and more complex, ensures the system's overall functionality, catching those subtle defects that unit testing might miss. Think of a symphony orchestra. Each musician masters their instrument, representing the meticulous work of unit testing. Then, the conductor steps in, harmonizing their individual talents into a breathtaking performance. That's integration testing, weaving those individual units into a seamless whole. Software development is much like this orchestral performance. It demands a harmonious blend of individual excellence and seamless integration. Neither unit testing nor integration testing alone can guarantee a flawless symphony of software. Instead, it's their synergy, their combined power, that ensures software quality. Unit testing lays the foundation, ensuring each component is sound and functional. Integration testing then takes over, guaranteeing these components come together, interact flawlessly, and deliver the intended functionality. Just as a symphony requires both skilled musicians and a masterful conductor, high-quality software demands both robust unit testing and comprehensive integration testing. By embracing both, we create software that not only works, but works brilliantly, delivering a delightful and seamless user experience.